Gravitational waves were predicted by Einstein about 100 years ago, and they are dynamical perturbations in the fabric of space-time, ripples in space-time, if you will.
The gravitational wave stretches space in one direction and compresses space in the other direction.
Nobody really believed that you could ever detect them because the size of the effect is so small.
I came to the conclusion that, yeah, if you made this long enough.
Nobody had ever made something like this before, so there was a lot of technological challenges that needed to be overcome.
That's what scientific discovery is really all about. You don't choose the simple things to do.
We have done something which is brand new.
The field has busted wide open.
It's monumental. It's like Galileo using the telescope for the first time.
I looked at it and I thought, my God, this looks like it's it.
Let me start with what we saw. So on September 14th, 2015, the two LIGO observatories in Hanford, Washington and Livingston, Louisiana recorded a signal nearly at the same time, nearly simultaneously, and the signal had a very specific characteristic. The characteristic of, as time went forward, the frequency went up. And what was amazing about this signal is that it's exactly what you would expect, what Einstein's theory of general relativity would predict for two big massive objects like black holes in spiraling and merging together. You see the two black holes, and the green that you see are the gravitational waves that are produced as the black holes orbit around one another. Their orbit decays and they merge together. All right. So they're spinning around. You see they're getting closer and closer together. As they get closer and closer together, more gravitational waves, they merge, and there's this burst of gravitational waves that travels for 1.3 billion years. It passes through everything. It goes right through matter, right through stars, and it eventually gets to the Earth. All right, and when it gets to the Earth, the gravitational wave passes, and what it's going to do is stretch and compress space as these waves pass. And you'll see that the Earth is jiggling like jello. I don't want people to be scared here. The Earth doesn't really do this. This effect is greatly, greatly exaggerated, but it gives you the effect. And then we zoom in, and how we detect these are using the interferometer that's in LIGO. And Ray Weiss is going to tell you more about the interferometer. I just want to say one thing, that the effect that we're trying to measure from these violent, these big black holes colliding each other at half the speed of light, all right, is so tiny that it takes something like LIGO to measure it. We are trying to measure things basically at 1/1000th the diameter of a proton. That's the size of the signal that you see on Earth from those events that take place 1.3 billion years away.
And we have been analyzing data from two detectors in Hanford, Washington and Livingston, Louisiana. LIGO built two detectors because we are measuring these tiny distortions of space-time here on Earth that you can only believe they're real if you see them both at the same time on places that are far apart. That's the only way to be sure that these are not local disturbances and they are coming from astrophysical sources. These detectors are L-shaped. This is the LIGO Livingston detector. They are 4 kilometers long on each side. That's a Hanford detector. And we have lasers that go back and forth between mirrors to measure the distance between those mirrors. And gravitational waves would distort the space-time and would be measured as distortions in that distance of 4 kilometers. Again, it takes a lot of people to do this, and you can see a lot of people, young people doing this, as well as people who have been working on this for decades. So this is it. This is what we saw. September 14 last year, we saw this signal in Livingston, Louisiana. That is a measure, that's a waveform that we saw. The units are strain, that's a distortion of space-time, and you can see a peak value. The largest value of this waveform was a part in 10 to the 21. For 4 kilometers, that's a tiny, tiny fraction of a proton diameter. That's incredibly tiny. But this signal is seen, you can see it even by eye, above the ever-present rumbling noise that we have in the detector. But we know it's real because 7 milliseconds later, we saw the same thing in the Hanford detector. This is it. That's how we know we have gravitational waves. But we know a lot more than that. You can see that these signals have oscillations that grow in frequency and amplitude and then settle down. And that's exactly the prediction that we know from solving Einstein's equations on computers for the coalescence of two black holes.
And that's the 1,000th the size of a nucleus. So how do we do it? Well, we do it by timing light. That's how we do it. And I'll show you this in this. Here's a Michelson interferometer, which is the device that does the measurement. And what you'll see see this round cylinder there, that's a laser. It's a make-believe laser. Then there's a beam splitter, which is that thing, which is a thin little thing in the middle. Then there are two mirrors, which have those black aspects, one to the left, one to the right. And then a make-believe detector, which is that rectangular thing. And now let me turn this animation on. And what we do is we fire light from the laser into the system. Now this is the electric field in the light. The color is the intensity of the light. So you'll see where the color tells you where the light is. But the electric field is indexed by the different colors of the field. And you'll notice the way this was set up is that right now there is no light at the photodetector. That's the trap you've set for the gravitational wave. And now people begin to wiggle in the animation, the end mirrors. And you'll notice light appears, disappears at the photodetector. That tiny motion and that fact, that light, the amount of light that goes to the photodetector is proportional to that strain in the gravitational wave. That's the method of the detection. Okay, now you're not done yet. You've got a device that measures tiny motions or tiny differences in time. But you're not done because you see those mirrors are sitting on the Earth, and the Earth is very noisy. It jiggles everything. And you want to make sure that the thing that jiggles the mirrors is only the gravitational wave. So we use all sorts of tricks. And I'll show you one of the tricks. Here's one of the tricks. What we do is we suspend the mirrors from a pendulum. Here's a sort of demonstration pendulum. And here's the mirror. And my hand will be the ground motion. And you'll notice if I move it very slowly or at low frequencies, the pendulum follows me. It follows the ground motion completely. Now let me wiggle it fast. And you'll notice the pendulum stands still while I'm wiggling. That's the basis of the idea. Now that's done with a tremendous elegance and with cunning in this picture. This is what's actually in the apparatus. You see it on the screen now. And that is now 4 of these things in series. Okay? And by the way, the principle I just showed you is very much like the principle in a car. It makes you comfortable in a Cadillac and sort of bumpy in a truck. Yeah? Okay. Now, the thing is, you're not done yet because there are other forces you have to worry about. And they are thermal noise, there's all sorts of noise, even quantum noise in this system. And all of that technology which has been developed, had it been available to Einstein in 2016, I would have bet that he would have invented LIGO. I mean, he was smart enough and he knew enough physics. He wasn't just a theorist, okay?